Okay, hi everyone. Welcome to the fourth Innovations in Digital Design webinar. Innovations in Digital Design, IDD, is an online platform for sharing innovative research ideas and design works in the digital design field. We aim to explore the nature and future of design by showcasing the outstanding works of young designers and scholars from all over the world. IDD operates once per month, offering oral presentations and discussions in English. All recordings are uploaded to YouTube and Bilibili and available for free to all. And today we're happy to invite Runjia Tian from Harvard GSD and doctoral candidate Ximing Zhong from Aalto University to share their recent papers presented at CADRA and ICADE about artificial intelligence in architectural design. So first, we're happy to have Runjia Tian to introduce his recent research of Enactive Genesis towards generative architecture with human-centric artificial intelligence. Runjia Tian holds a master's degree of design studies in technology from Harvard Graduate School of Design and a bachelor degree in architecture from Harbin Institute of Technology. Currently, he is an AR effect engineer at TikTok, working on TikTok's AR effects platform in Effect House. Welcome, Runjia.
Thank you, Wei, for the introduction, and thanks, IDD, for the invitation and the opportunity to share like my previous work and understanding about like architecture and AI in general with the CAD community. I'm gonna just can everyone see my screen share now?
Yes.
So okay, cool. Then I'll just get started. So today my topic is I slightly rephrased the title called from Enactive Genesis, which was the title for my thesis at the GSD MDes program, to generative game, because I think generative game is probably like a more generic framework for this sort of like exploration for generative architecture using AI technologies. This was what I work on as my like thesis at the GSD, which is like the conclusion of my explorations of using neural networks for generative architecture. So at the beginning, it's a very simple question, and also the motivation of the thesis is that as architecture students who came from like more of like science and like math background during my high school, I sort of like had a time struggling to understand the design process because it doesn't have any explicit knowledge or formula that you can follow to generate like the architecture designs. But instead, you learn them explicitly through a almost like a apprenticeship working pattern where you learn by doing the design and receiving critiques from the domain experts like your like instructors. So I have always been wondering this question, like how do we design architecture? So obviously the question centers on the word design, how we think about the design activities in our architecture. So I would like to borrow the concept from cognitive neuroscientists, because I'm generally interested in like the cognitive aspect of architecture, as well as the like there was a like a like also I think this idea also kind of like impacted by the trend of computational neurocognitive science studies at which was in this which was kind of like a blooming studies in across Harvard MIT when I was studying. So like as designed by one of the cognitive scientists, the design activity is like a human cognitive activity of finding solutions for a vague problem. So it sort of like differs from the like our inference problems, and also but it's also like we have other like common tasks that rely hugely on our common sense, and also which is our yield post problem, where computer science they call them is like you can't really define the like process explicitly, but rather it relies a lot on the a priori knowledge and also like experiences and other like things that are not like formulated or easily designed. These are easily defined by like those explicit knowledge we have. So so how do we study those kind of like questions or like human behaviors? One of the like aspiring research trends at MIT CCL was they call it this process to reverse engineer human intelligence. This concept was long ago proposed by like David Marr, also a computational like a neuroscientist. So he proposed the interesting like thesis that to study a human activity using like AI, you don't usually start from the biological aspects, so which was like a typical research methods. But instead, as someone, I believe he's from computer science background, so he proposed this new methodology of studying brain activity from computation to the implementation. So instead of studying the biological foundations of how you see the world, how your the cells inside your eyes works to perceive the lights and lights and rays and things like that, he first proposed a computational model of human vision. Like as we all see today, like we have like a wide variety of different neural networks for image cognition or object recognition. And then after we have this kind of computational model, we propose the algorithms to achieve certain tasks. And using these algorithms, we can reversely infer how human brain works. Yeah, I would like to say that this thesis has its own drawbacks, but I think brings a new aspect or new idea to the to our design domain as well. It's like instead of studying how cut into our brains of how you actually do the design using your brain neurons, why don't we just propose a machine that can achieve those like design tasks using whatever like computer science methods, and then we can sort of like infer how human design architecture as well. So this is like the ultimate goal of why I started this thesis, and yes, because of my like interest in how design functions or how we design as human being. Yeah, but to achieve that, we have to use a computational approach first for now, because because it's probably easier to modeling the process and achieve those tasks. Then it's probably faster than actually doing the brain studies of those activities. Yeah. One of those examples that the computer science people use and has achieved those results is the object recognition and computer vision. So they develop like a lot of like object recognition models, and after those, they're using neural networks for those models obviously, and then they decompose those middle layers of the neural networks, and you can see that it kind of like reflects how the machine recognize whether something is a cup. First, it has some like high level information of the object's edges and the overall like layout of the images, and then it kind of like recognize the materials and textures and colors and radiance of the images to as in the lower level of the neural network. So yeah, this sort of like inspired me to think about like how those computer scientists use the machine vision as an example, how we can like use this approach in design domain as well, for architecture design as well. So I'm thinking about what if we can propose a computational model of architectural intelligence, and then we can infer the neurobiological foundation of the architecture intelligence, and then we can learn how human actually do the architecture design. Yeah. So to realize this vision, it's definitely a vision because we don't yet have a machine that can do this task, right? And to realize this vision, we I think the important thing here is how we design this machine, or in another way, like what we are interested in is how to develop an AI that can sort of like design things or generate designs for us based on the conditions we provide to them. So before we start to how we implement the machine, I think we can take a look into how we design those kind of like machines in the first place. Like borrowing the concept from the Alan Turing's work, Computing Machinery and Intelligence. So where he proposed a famous imitation game, which also known as the Turing test, in the later years. He proposed the model that the methodology to test whether a machine has surpassed human intelligence in a way such that if you put a machine and a human in two different rooms, and you then give them different tasks, for example, translation, or generate some passages given a task, given a topic. And if the results from those two different rooms differences cannot be told by like a human being, then you can say the machine passes the Turing test or passes the imitation game. So I would say the imitation game is sort of like the ruler or the kind of like a standard to measure the intelligence of general computational machine. But for architecture, what is how should we address the imitation game? Because architecture is sometimes like it's not a definite process, and you have those like the typical design process, like you have some environment, like the variables or like description about your design tasks. And after some, for now, it's still a black box intelligence that we don't yet uncover what's inside it. But you always spit out some outcomes or designs, iterations based on those environment variables. And since we always call those for historical reasons, we'll call those like a process like a generative design or something. So I would like to propose this machine to be called generative machine. And those imitation games for those generative machines is the generative game. That's where this topic of this come from. Yeah. So in any case, I would like to say that this is like my personal approach to kind of like propose a methodology, or like a generic methodology for like architecture and AI. And the structure of the generative game, I would like to say that I quoted Michelle Williams, which is the founder of MIT Media Lab, and also the he wrote a really like awesome book about architecture and AI. And he also proposed the first theoretical foundation of the CAD, which I think is one of the first articles in the CAD industry, is that any of the CAD system can be seen to composed of three parts: the representation system, the generation system, and the testing system. So the representation system is a data structure we use to represent our designs. For example, if we use the random models, it's the 3DM file, and it using the BREPs to represent our designs as the geometries. Or Revit, we have like the Revit files, and those like beam files, and it's actually just data, right? And for generations, this is the interesting part. And this is where the actual intelligence came, is that how you use algorithms to generate the environment variables into outcomes. This is actually the most complicated part as well, or the most challenging part as well. And after these, you have the testing system it's just like how you measure the success of your generation. A lot of the so-called generative design or AI generative architecture designs follow this kind of like pattern. Here are some of the early studies that this is one is I believe it's from the Autodesk Autodesk generative group or something, and they used what is called it's like profit and solar energy to measure whether like a certain rules generated like urban layouts can be optimized. They were back it was like back in 2018, and they were still using the genetic algorithms and it's sort of like a rule-based algorithm to optimize the results of like the urban layouts. But then we have neural networks. Instead of like using explicit rules to represent the design process, you can now kind of like sample a distribution of the designs from a data set that you provide to the machine. And this approach, we typically call it implicit approach of learning. This is kind of like, I think this dates back to to Turing's passage, the Turing's important article, Computing Machinery and Intelligence, that instead of trying to produce a program to simulate the adult's mind, so we can produce one that simulates a child's. So it learns from scratch, it builds its own understanding of the world based on the data you provided to it. So it probably can think differently as human brains. This sort of like you can see that the human and the machine intelligence sort of diverge here, like from David Marr's proposal. But I think that's absolutely fine. So like it doesn't have to be one-to-one mapping or like exactly the same, but it's still this kind of like inspirational approach still works for the journey of AI in architecture. Yeah, and after the invention of neural networks, and after we have enough computational power to democratize those kind of like neural networks, we a lot of like research in CAD industry began to pick up neural networks in generative architecture designs. So, for example, the GSC graduate student like famous architect ArchiGAN is one of the first using the like, I think back in that time it was still kind of like called StackGAN or something, like you stack multiple layers of like multiple layers of pix to generate architecture like designs. Yeah. And also there are other representations using neural networks, such as using the convolutional message passing network, which was a kind of like graph neural network to translate a like function layout graph or program graph to a floor plan layout. This was one of the ECCV papers published by Autodesk Research Group. So they were using the conv-MPN to generate layouts based on the input graph. Yeah, and also you can represent things in voxels or point clouds in the 3D formats. But I think because we have quite limited 3D data, like those kind of like research are still in its early stage, even today. Even we have NERF and all this kind of like cool like 3D generation, it's still the amount of data we have in 3D compared to 2D is still like not on the same level. Yeah. Yeah, after we see like all those advancements in AI in architecture, yeah, typically in a machine learning course, we always, or a computer, like, yeah, in machine learning course, we'll always ask these questions: can we do better? Yeah, so the problem, there are a lot of problems for the existing like approaches in both rule-based systems and also those neural network-based systems. In the sense that it can be divided into different aspects. Like, for example, for the representation, it's not usable in real world. It's not like universal enough. Like, for example, the ArchiGAN images, you cannot directly convert that to a usable model like or a usable Revit file. And it's not using any like human-centric evaluation metrics. You don't take into the you don't have a way to measure those like metrics explicitly, and because they're for like the pixel base is basically sample the distribution of images from your given data, and it just learns, it just takes whatever it has in the data, like even some bias to the generated results. Yeah, and more importantly for the generation system, like is either constrained by rules or like those neural networks, like they are sort of like they're not scalable and not, you cannot add any other like metrics to them apart from the predefined like pix-to-pix methodology. Yeah. So how can we improve this? So for the representation system, I would say like one interesting thing that one thing that caught my interest at that time was that why not we use like a beam or sort of like semantic like graph or other data structure to represent the architecture then, because Revit is just, you can define the elements of the architectural you can define the architectural elements by using the type of the objects and also the location of the like the location or the actual dimension metrics of those like architectural objects, and together they can generate a graph that you can one-to-one mapping the architectural design to a data structure. So beam is sort of like the very precise representation of the architectural design itself. Yeah. And for the testing system, we don't really have any measures, have any ways to do that in a human-centric ways. Like we don't really evaluate the quality of the space that gets generated from these neural networks in 3D, right? And is no way that we can take into the like domain knowledge of human experts to optimize the neural networks using pix-to-pix or other like image-based approach. Yeah. So that something that I take inspiration from is also from the like the infant's learning process. Like there are like multiple representations of the like infant's learning process. One of them, I think, is inactive learning, what is called inactive learning. So it's sort of like experimental worlds by actually using the objects. For example, they learn the intuitive physics by throwing the objects around, and they see that it bounces against the wall, so that the infants gotta learn that, oh, like these objects is sort of like a collider, or it collides with each other, and it stops. So like that's how we get the intuitive physics, by manipulating the world or interacting with the world. Yeah. This is kind of like similar to the another almost another notion, or another paradigm of learning, is what we call reinforcement learning. So reinforcement learning doesn't like learn the data in a sort of like in as I will call those like a previous learning methods, representation learning. It's not my personal like way of addressing it. Also, like some people call them representation learning, because they are basically learning the representation of your designs by sampling the distribution of the specific like elements from your datasets. So, but reinforcement learning is sort of a difference. It assumes that you have an agent, which is the AI itself, and it has an environment, and the AI interacts with the environment and gradually learns how to like perform actions to change the environment, and and obtain some rewards. So one of the interesting examples is for sure the AlphaGo game, that it uses for like tree search, and also I forgot what exactly the algorithm. Sorry, the neural network was probably PPO or something. And also like it has gained a lot of like superhuman intelligence performance in a lot of like aspects, such as the Atari games. And you may also heard that recently they also beat the human players in tactic games such as Dota, or or like more complicated games. Not to mention the AlphaGo games that beats these adult. Another interesting example in the inactive learning or the reinforcement learning process is also the paper by OpenAI from 2019, is that they train the agents to play hide and seek. It's actually a paper about like a multi-agent like reinforcement learning. So you can see that interestingly, the agents gonna gradually learn to steal away the letters so that the enemy cannot catch them, and so that they can lock the doors. So this is like a really interesting like observation, such that you can see that we can probably train AI to manipulate the environment, or to assemble certain architectural elements to achieve certain results that we want them to achieve in terms of the architectural quality. So this is a really important precedent study, the like multi-agent machine learning paper. I would say this is probably like the most important paper, like in like the actual most important paper that I got inspiration from during my time. This reminds me, like later on, there was some other works of like for example, from Autodesk, to learn how to assemble certain like industry design objects based on the command set, and also using reinforcement learning. Also in 2021, there was another paper called Design Spatial Assembly, which used reinforcement learning to assemble architectural elements together to achieve certain results, or to surpass certain like evaluation metrics. Although they didn't, I don't think I saw how they defined the design metrics, but the evaluation metrics. But I think this is an important paper as well. Like it shows you how we understand architectural as fabrication and assembly, or assemblage of architectural elements. And in this sort of like representation, it's still learning the representation, but it's not learning the drawings of architecture, but instead it's learning the tectonic aspects of architecture, using the intelligent assemblage agent. Also another like something that has also been in my mind was Bernard Rudolphi's book Architecture Without Architects, is that in a sense that the early vernacular architecture in the human civilization, they don't really have like esteemed architecture. So these sort of like, but those architecture spaces had quality. And we can see those architecture as those like a total image picture of architecture of human intelligence, where our ancestors learned how to manipulate the environments or to assemble different elements from the environments to create a shelter such that it can shelter people from the harsh of the environments and to live a better life. Yeah. So this way of thinking, or this like ideology of architecture that sees that as a assemblage or like architectonics approach is sort of like what's the foundation of my paper, Enactive Genesis. Yeah. I think I'm a little bit like behind my schedule, but I'll probably, so the rest of it is just like technical aspects of how I actually implemented this reinforcement learning environment. I'll probably go through some of the parts quickly, and you can probably ask more in the Q&A sections. So therefore, after analyzing those like contents of representation learning and of architecture, I proposed this kind of like what I called Enactive Genesis during the time I wrote the thesis, that we can create enactive learning environments using reinforcement learning to train an intelligent agent that manipulates a grasshopper beam assembly script to generate a space. And this space can be evaluated by another AI agent in Unity that navigates in the space and spit out a rewards of this or evaluation of the space. And these rewards is then fed back to the generative neural networks that manipulate the GH graph to optimize the generation such that the rewards can be higher. Yeah, this is a little bit like not so straightforward, but you can think of the process like here is like the stupid AI agent at first. You throw the stupid AI agent into like a mass of walls and columns and slabs in the 3D world. Then it sort of like constructs a space using those elements you give it based on a certain commands. And then after it finished the construction, it walks around the space and give you a rewards of the space. And then it will also use the rewards to optimize its next construction so that it can improve itself over time. Yeah. So I think the generative beam part is straightforward. Like I just create a grasshopper library that have several APIs, such as you can create the 3 elements of architecture inside the space. You can create a wall by specifying starting points at any point. You can also its height in the later explorations. You can create a column by specifying its location, and also a floor plan or a slab. Sorry, it's a slab. It's actually called a slab inside this structure. And using those simple elements, it can generate architectural spaces. So, for example, this is one of the experiments I created for trying to replicate the plan of the Barcelona Pavilion by Miss Monroe, where you place like several columns and walls, and then you generate the architectural spaces after certain steps. Yeah. So to do that, I created this Grasshopper library, and it sort of like has all these implementations, and you can generate the walls and columns, and also has the API to add a column in certain places in the space. Yeah. Yeah, you can see these are some of the experimentations I did. So the number of the walls and columns are actually indefinite because it's sort of like the parameter that the agent is gonna learn during the process. Yeah. These are some of the results that I generated. And after it generates the space, it's gonna walk around the space and spit out a like evaluation of the space based on 2 metrics I give it. So first metric is the accessibility of the space. Like I first do a division of the space and generate a Hamiltonian path of the space. And the agent gonna just follow the Hamiltonian path and traverse the space in a non-repetitive pattern, so that it visit all the sections of the space for only once and only once. And after it visits the space along the Hamiltonian path, it generates a score. So of how many like areas of the space it has visited. So this shows how the accessibility of the plan, like whether you have some dead areas where you cannot access. And on the other hand, I create another like test matrix to measure the transparency of the space. Yeah. So this part is like you can understand that as it sort of like takes the phenomenal aspects of architecture to experience the space in the first person point of view. Yeah, as you can see in this example, the agent is trying to go across the wall, but it can't. So there are some areas of the floor plan that is not accessible. Then it's sort of like a reduce the score, the reverse of the generation. Yeah. This is like how I compute the Hamiltonian paths of the floor plan. And now comes the interesting part is how I compute the transparency of the generated space. So this was very speculative, I would say. Like it's sort of like not like a very it's not mathematically proven approach, but it sort of like translates the definition of Colin-Rose transparency in a mathematical way. How I compute the transparency of the space is by taking its depth image, and then compute the edge of the depth image. As you can see here, the transition from a like a close point to a deep point is sort of like represents that there's another space behind the interface between you and that space. So take this kind of like space that Colin Raw referenced in one of Corbusier's drawing. I forgot the name of the house, but this is one of the example Colin Raw explicitly referenced as a good example of spatial transparency. And the way that I interpret it, and also by his writing, is that Colin Raw defines transparency as the coexistence of two different space of different depths in the same perspectival view. So those edge in the deep depth map represents the number of transitions or the amount of transitions between the spatial depths in the same perspectival view. Yeah. It also includes the like it also includes the literal transparency and also the phenomenal transparency. I didn't differentiate between those, but it sort of like represents both. So therefore, I do a depth detection of the edge detection of the depth map, and sum like all of the those white values or the edge values together to get the transparency of that particular frame. And after that frame, I sum the average I sum all the transparency like rewards and get an average score of them over the traversal of the in the space to get an average rewards for the spatial transparency. And this is the testing part. And for the generation part, the agent uses the proximal policy optimization algorithms to learn a neural network that speeds out the generation step one by one. So for example, like this is the example to generate a wall placed at a column placed at the location 5050 with a height of 3 meters. This is how it generates the first comments, and also for the wall. So for the column, it generates at the location 5050. And has a height of 3, and the column and on the wall, for the wall example, it generates a wall at 0.127 from 0.01 to 0.27 and has a height of 5. This is how I represent the entire system. And as you can see, each of the generations that can be represented with a like a 5x1 vector, and the neural network learns to predict the next like value of generation based on the history of the generation, and also the rewards that it gets from each generation epoch. from each generated apple. This is sort of like the training process of how the agents navigates around one of the generated spaces after the space is assembled by the grasshopper component. It's sort of like very speed up. So there are some other experiments that I did. So first I tested that on the 2D spaces, but it seemed to struggle a little bit in the generation step because like there are just too many like little transparency elements. You might have more columns in scattered around the space that can create this kind of special transparency, but it doesn't create any phenomenal transparency as a result. This is the training process for the 2D part. It doesn't really converge really well. And things get really interesting when it comes to 3D. Like as you can see at the end, it just generates like a long wall and several columns. So those can generate a lot of edges for sure. And for the 3D part, that's where the really interesting part comes in, because you have more like variations of your design, such as you can have a floating slab on top of a column or on top of a wall. So this in this presets, we can see a lot of like interesting like results after like certain training steps. So first of all, it's still like a huge mess, and a lot of the spaces are not even accessible at all. But after like a certain period, you can see that it has more walkable spaces and more floating slabs as a balance of the accessibility scores and also the having like enough edges for transition of depths between spaces. And after 700 episodes, I didn't have enough time to train this further due to the limitation of the projects. It generates like this kind of like spaces that has more floating slabs and also some like columns, but with like far less walls, so that it sort of like has this kind of like transitional spatial depths inside its perspectival traversal. That's basically the outcome of my thesis projects. And I created this. I also made it like sort of like a human AI cooperative game where you can also like manipulate the generation of the game using, you can call the APIs of the you as a human, and also you can let the AI to generate the results as well. And it's showing the weird edge detection of the depth map in real time in this two huge billboards. That's pretty much I have to say today. And I think one thing that has always been my inspiration of starting architecture and AI is this Alan Turing's work. And I think the way he thinks about intelligence is really like fascinating. And I would like to end my presentation with the quote from Alan Turing as well, that presumably the child brain is something like a notebook as one byte from the stationers, rather little mechanisms and a lot of branches. So I think this way of having less predefined notions or having less restrictions of explicit knowledge about AI agents is sort of like really like groundbreaking in terms of the research process. You can find this paper in the digital access to scholarship at Harvard. It has the full paper posted there. And also feel free to connect on all these social medias, like if you want. I wanted to thank the IDD organization again for this invitation and this great opportunity to share my understanding with you all and to like communicate our thoughts about the generative AI in general. And so thanks for watching. That's all from my part.
Thank you, Runjia. I think it's really incredible, and I'm personally really intrigued by how you compare how you testing everything in Unity instead of only like doing experiment in Grasshopper and Rhino. And I personally have a question because you use human-centric ways in Unity to examine all these like generated floors and columns, but like the way you use it is like you experiment with the transparency, but only this way is actually for the machine. So it's not you're using real people that examine this thing through VR in Unity, but you actually use machine to generate a rule that depends on all kinds of depth detection about the transparency. So you're actually using a machinery way to do like human text. So what about your next step? So are you going to improve this?
Yeah, thank you, Wei, for the question. Yeah, I would like to say that so I think this system itself is probably like in its essence a like flexible or like something that you can plug different evaluation metrics into. That's why I used reinforcement learning and also create this first very simple rules of computing the like transparency or accessibility, because you can add other metrics such as the energy efficiency or the lighting or other perceptible like metrics. For example, you can add a real humanoid avatar into the scene and also compute the comfort at the humanoid avatar during the runtime. So that's what I think is really interesting about using reinforcement learning, that is you can add different other metrics to the reward function. But you might also like practically you might also want to break this training task into different parts so that it can convert easily. Like for example, using like a method like curriculum learning so that it can learn different objectives at different stages, and yeah, and spit out one general agent. So yeah, that's sort of like my thoughts about how this can go in the future. Like you can definitely plot more rewards functions or evaluation metrics computationally to this to this like methodology. Yeah.
Yeah, looking forward to it. Any other questions?
I have a question and a comment. Firstly, I just have a comment for your presentation. Thank you for the detailed introduction. But I think there are 20 minutes is a little bit too long. So you understand? And another thing is that could you please repeat your contribution of your research?
Yeah, so I think the like for this thesis it doesn't really have enough evidence of like to prove that it works well for the conditions, but generally is I think for the 3D parts it generates it's kind of like biased to a certain level of generating the more slabs and more floating slab, and also how to say that the like intercepting columns or walls so that it can have more transitions of depths of more transitions of depths instead during its traversal process of the floor plan. Yeah, that's sort of like the conclusion of this paper. Yeah, it's learning from a random states of generation and then sort of ends in a sort of like a derivative design direction. Yeah.
So from my point of view, you just proposed a new model or a tool to solve the problem, but actually the problem maybe I have another simple problem. What is the problem you solve?
Yeah, I think as a thesis project, it sort of like doesn't really solve any practical architectural problems, but rather propose a new methodology of generative AI or generative architecture. Like, yeah, so it assembles the different, it sort of like actually creates this environment of training the assemblage agents in using the game engine. If you mean that's what the research problem. Yeah.
I think Runjia is more to provide a game engine like Unity or other like human-centric environments to re-examine the grasshopper generate architecture elements.
Yeah, so if you're familiar with like reinforcement learning researches, this one is sort of like similar to the Munjuko simulator that UC Berkeley proposed for a lot of like intuitive physics training environment. So yeah, it's actually it's sort of like a foundational level of stuff that it builds the toolbox or sandbox for reinforcement learning environment in architecture. Yeah. But we don't yet have that sort of sandbox. Yeah, that's what the main research question was, I think. I didn't have enough time to turn that into a research paper, unfortunately. Yeah, but yeah, if this is not like a paper because it's more of like a thesis project and more explorative. But I think, yeah, thanks for bringing this up, Albert. And think, yeah, to make it a paper, it definitely needs to have a more clear definition of the research problem. And yeah, thanks so much for the comment. Yeah, and really apologize for the timing. Sorry, I thought it was gonna be like 1 hour or something. Yeah.
I have a question, Runjia. Thanks for your introduction about the deep learning part. And my question is about the beam system. And it seems that you build representation data structure with a beam structure. But is there any link with a different architectural element with each other? I mean, a message passing network, something like the message passing network in GN, the edge link. Do you understand my question?
Yeah, I didn't yet have enough time to build like the comprehensive beam system, but I only built the it's sort of like I wouldn't really call it a beam system today because but it's sort of like a symbolic system where you it's representing the command side of the generation in some way, like I would rather call it like a procedural system or a like a procedural DSL for the architecture. It's not necessarily like these beam system as we see today, like the IFC like data structure or like the Revit. It's not a comprehensive beam system. It's just representing, taking concepts from beam that you can use the parameters to represent the architecture elements. So yeah, I will actually call it like a parametric like procedural DSL for architecture spaces. Yeah, but
my question is do you think it's very important to make a hierarchical relationship between the elements? Do you think in this way it's better than just with a parametric ways? For example, you use CN, the convolutional ruler can make some connections with your neighbors and the element, and you use GN. There's a message passing network, but in your beam hierarchical data representation part, there's no link between the element and element. And when you get the loss of your loss function, reward function, there's no message passing from this element. For example, I moved this room to another side. There's no message passing from this room to its neighbors. Do you understand my question? It's hard to explain in English.
I know, but so why this procedural grammar is sort of like it's not having that message passing or I know what you're trying to represent. It's like the the spatial relationship between the different like elements of the data representation. I will argue that for this part, like since this is like a reinforcement learning process, and to my generation agent actually takes in the previous commands when it generates the next step. It's sort of like a autoregressive pattern that it takes in the previous steps to predict the next step. Yeah. So and also the reward function, it's like when you're doing the gradient descent, the reward function will also like optimize the it's not exactly like recurrent neural network, but it's sort of like it has it has sort of like optimized the gradients of the previous step as well. So it's not only just generating a random step one at a time. Yeah, that's why I would say the sort of like the implicit relationship. But I think this is not the optimal representation as well, because it's for now the procedural grammar is just such a small data set, and it's such a small chunk of generation, and we should have take into consideration more other elements as well, like windows or other openings, and yeah, I'm also trying to find the optimal representation. I think that's a sort of like a ongoing discussion as well. Yeah.
Okay, thank you.
Okay, and there's one more question in the chat. So the pipeline is generating models from Grasshopper and then import them to Unity for under testing automatically. And I'll say yes. And what's the related library in Unity for reinforcement learning in this process?
Oh yeah. So for Rhino Grasshopper ICP, there's something called Rhino Inside. So like in the latest version of Rhino, you can plug Rhino process to something else, like the either Unity or Revit. That's how I do the ICP process. IPC, IPC process between the two applications. And for Unity reinforcement learning, it's just using the ML agent of Unity. So it's sort of like open source library for reinforcement learning. It's using its own like machine learning frameworks called Barracuda, and yeah, that's how I did the reinforcement learning part. Yeah.
Okay, thanks, Runjia, for all the presentation and Q&A section.